so let's hope our friends turn up and get going. So we move today closer to the applied computational side of the mathematics, and we consider the operation that if you were to become computational chemist, you would actually do every day. And you would do it every day even if you're a radio astronomers or acoustics specialists, signal processing specialists, or just about anything in physics really, because the operation is so central to the modern computational sciences. Now, you actually seen this operation already, you just didn't know it. Remember those old music players? They had, particularly the sophisticated ones, two types of display. One was time amplitude, and you essentially saw some kind of frequency being displayed on it. And the other was those strange jumping bars, where you would see amplitude, but not as a function of time, but a function of frequency. And so you would have, at some frequencies, your music would be loud, at other frequencies it would be quiet, some other frequencies would be absent entirely. And you had these red-topped jumping bars, and you intuitively knew that the bar on the left corresponds to low frequencies, and the bar on the right to high frequencies. And so the transform that the machine does internally to convert a representation like this into a representation like that is the topic of our lecture today. It's called Fourier transform. So we will introduce it first formally as an integral, as a mathematical transformation, and then we will take a look at the physical meaning, particularly at the applications that the thing has in image compression, sound compression. So JPEGs and MP3s are one of the application areas of this. Okay, so item 1 on the agenda for it. Formally defined as the following pair of integrals. So this is your, let's say, f of t, and that is your f of omega. And I will use the same f, I would simply differentiate them by some argument. So they're different functions. F of t is a function of time, and f of omega is its image in the frequency domain. Okay, so our f of omega is 1 over root 2pi integral from minus infinity to infinity f of t e minus I omega t dt. A rather obscure integral, as you can see. It will become clear what it is, perhaps more clear, once we consider scalar products and function spaces a few lectures down the line. But for now, just take my word for it that that is Z transform. And then, of course, it's intuitively clear that in some sense these two representations of this signal are equivalent, that this contains the same information as that. It can be proven rigorously, of course, in mathematics for chemists. We don't have the time for those proofs, but there is an inverse transform that takes a frequency representation back into the time domain. And it's very similar. So f of t is 1 over root 2pi integral from minus infinity to infinity of omega e minus, in this case plus, I omega t d omega. So that accomplishes the forward transformation, and this is called the forward Fourier transform, f t plus, and that is called the backward transformation, f t minus. Occasionally, operator notation is used as well, so you can say f plus with a little hat that signifies an operator applied to f of t equals f of omega, and then f minus, likewise an operator acting on f of omega returns us the f of t. So this is the formal definition of a Fourier transform. Let us now take a look at one example, and this example will make clear these relationships that we've just seen. So let us take something that is quite typical of acoustics. So if that's T and that's amplitude, let us consider a signal that just oscillates and the oscillation decays with time, something like this. You can see that we have a complex transform. In fact, it helps with mathematics to convert all our trigonometric functions into complex exponentials. So what I will have here is E I omega 0 t, where omega 0 is the frequency of this oscillation to distinguish it from a polar variable. So that is the oscillatory signal. And I will multiply it by a decaying exponential minus kt to make it decay. So you remember from your chemical kinetics that that is just a decay. You remember from your mathematics that that's an oscillation, cosine plus I sine. It's the real part of it is the cosine, so that's the signal. So let us take this oscillatory and decay function and calculate the Fourier transform of it and take a look at what we get. So our f of t is going to be e I omega naught t e minus t, a decaying oscillatory signal. Then f of omega is going to be that integral. So one thing I should note is engineers use different prefactors here. So be careful when you are using various software packages. In some cases, the forward one is 1 over 2 pi, and the backward one doesn't have results. But our definition is mathematician's definition, the so-called unitary transform. Okay, so 1 over root 2 pi integral from minus infinity to infinity. And then take a look at this function here. We began it at 0, so there was nothing in the negative half plane. So there's no point taking this integral from minus infinity. We just put a 0 here and integrate our function. So we put the f of t here, e I omega naught t, e minus t, e minus I omega t, t. Bunch of exponentials, all very straightforward. So what I will do first is I will merge all of the indices and I will take time out of the bracket. So 1 over root 2 pi integral from 0 to infinity e to the power of I omega naught minus k minus I omega t dt. We know perfectly well how to integrate exponential functions. We will have this entire bracket popping in the denominator, and then the rest of it will remain unchanged. So 1 over 2 pi, 1 over I omega naught minus k minus I omega, and then exponential of that same thing, I omega minus k minus I omega t from 0 to infinity as per the Newton-Leibniz formula. Okay, let's take a look at what this is at infinity. Well, we have a decaying oscillation, so at infinity it simply goes to 0. At 0, the exponential is equal to 1, because exponential of 0 is 1. It's basically 0 minus 1, so we just pop a minus in front. So it's 1 over root 2 pi, 1 over, and I will just absorb the minus underneath the exponential. So we will have k, and then plus, and we would have that with plus, so omega, and that with a minus omega. And there should be an I in front of this. Okay, so far so good. We got some sensible looking function, but of course it's got the I in the denominator. Not a good thing, because it's hard to interpret. Let us use our knowledge of complex numbers to separate the real and the imaginary part and take a look at what's there. Now, you remember how to divide complex numbers. You multiply and divide by the conjugate. So here we would have k minus I omega multiplying and then also dividing omega. In the denominator, we have a complete sum of squares. In the numerator, we just have what we have. So it will be 1 over 2 pi, then k minus I omega minus omega naught, and in the denominator, k squared plus omega minus omega naught squared. Okay, and finally separating this into a real and the imaginary part. So the real part is going to be everything without the I, 1 over 2 pi, k over k squared plus omega minus omega naught squared, and the imaginary part is the rest of it, right? So minus 1 over 2 pi omega minus omega naught over k squared minus omega squared. So far so good, but quite obscure as you can see. Let us consider this therefore graphically. So if we plot the real part of that Fourier transform as a function, of course, now of the frequency, because this is our Fourier transform, let's think about what this is going to be. K is just a positive number, right? It's the decay constant of our signal. It's how rapid this oscillation decays. In the denominator, imagine that omega is very far from omega naught. Either very far positive or very far negative. The square would be large. The denominator would, of course, also be therefore large. The entire function would be small. So far away from omega naught, we have small amplitudes. Then as we are passing through omega equal to omega naught, this is equal essentially to 1 over k with the coefficient in front. And as we approach, the denominator gets smaller and smaller, so we have a peak. And then as it departs further into positively decays again. So what we have here is something called Lorentz function, and it's a peak that looks like this at the frequency omega naught with the amplitude that's related to k. And this is very important, and this explains why all of that acoustic equipment had all those jumping bars. Look, we started with a particular frequency here. We Fourier transformed it, and we got a peak at that exact frequency. So mathematically speaking, therefore, because all the transformations that we have here are linear, what is going to happen if you feed an arbitrary oscillatory signal, radio waves, acoustic waves, music, even some color distribution and some image, and in the time domain, it looks like just some non-discrete oscillation. If you take the integral analytically or numerically, you will more or less have a table of frequencies with the intensities of these peaks being related to the decay constant. So look, if we have here omega equals to omega naught, then this is 1 over k, and so the slower the peak decays, right, the smaller the k, the sharper the peak is going to be. So rapidly decaying oscillations correspond to broad peaks, slowly decaying oscillations to sharp peaks. This is actually the foundation, for example, of nuclear magnetic resonance spectroscopy. If you've ever done any organic synthesis, you must have seen an NMR spectrum, which would be a pattern of exactly such peaks. And in fact, the way it is recorded in the instrument is in the time domain as these oscillations of the magnetization that precesses around the applied magnetic field. And then we apply the Fourier transform to get the pattern of peaks. So that is the mathematical definition and the rough physical explanation of what the transform is. Of course, in your practical classes, Chris will teach you how to take that numerically. You've already had all the integration methods that you need, all the way to Simpson, and I think actually even Gauss-Legendre was mentioned. And so now that you know how to integrate, you should be able to take the integral. Good luck with infinite limits, that will get interesting. And so forth, you should be able to do the Fourier transform numerically, eventually in your classes, and analyze oscillatory signals. Okay, so let us now take a look at the properties of the Fourier transform. I've already mentioned one, that these two transformations are each other's inverse. This is a subtle fact. Proving it would rely on delta functions, which we do not teach chemists. So I will simply give that fact without proof in the handout, that when you apply that transformation first and that transformation second, you get your original function back. So the two transforms are each other's inverse. Second thing, that is super useful because it takes the pain out of solving differential equations, is the fact that Fourier transform replaces differentiation by multiplication. Imagine you had some terrible differential equation in the time domain. Turns out, if you Fourier transform both sides, differential equations, quite often, if you can get away with taking the integral, map into algebraic equations in the frequency domain. So let me show you one example of that. So if we take a Fourier transform, so f plus operator, so that the integral operator there, acting on f prime of t. And I will take a one-sided Fourier transform, so it's only from 0 to infinity in this case. So that is going to be 1 over root 2 pi integral from 0 to infinity f prime of t e minus I omega t dt. Well, we have an integral, and you remember the integration by parts that would allow us to actually pop this derivative off. So what I will say is, in the integration by parts scheme, u is e minus I omega t, and therefore du is minus I omega e minus I omega t dt. I just differentiated that. Then dv will be f prime of t dt, and v is therefore f. Okay, so assembling that stuff together, so we have uv, so f of t e minus I omega t from 0 to infinity, minus v du, that minus is already there, so it's plus I omega integral from 0 to infinity, f of t, and then the exponential f t e minus I omega t. But notice that and we should remember to put 1 over root 2 pi around that. Notice that this is actually the Fourier transform of the original undifferentiated function. And so we can conclude, after a bit more philosophy, firstly, look at that. If we go to infinity here, we assume that these functions are well behaved and integrable, so they have finite support, therefore they must go to 0 at infinity. So at infinity, at the upper limit, we have nothing. At the lower limit, we would have exponential equal to 1, and that is just f of 0. So minus 1 over root 2 pi f of 0 here, and then plus I omega, and that, always 1 over root 2 pi, is the Fourier transform of the original function. So that is plus omega, and that's f omega. So notice that what was previously a differentiation operation is now just a multiplication by the frequency. And so in a lot of situations in quantum mechanics, remember that the momentum operator is a derivative. Applying the momentum operator in the frequency space is considerably easier. And so a lot of quantum chemistry simulation packages, they alternate between time representation and frequency representation, because in the time representation, the coordinate operator is easy, you just multiply by x. And in the frequency representation, the momentum operator is easy, just multiply by the frequency. And so they just alternate between them, and therefore never have to do any differentiation, only multiplication in that case. Okay, so let us now put this to good use and consider, for example, chemical kinetics. So, and it's quite simple. I will only look at first order kinetics, but you can imagine how that can be extended to other cases. So let's say we have a substance A, and then D concentration by dt is going to be minus K A of T. And all of you remember how to solve such differential equations, and all of you vaguely remember that they have been quite problematic, particularly when they proliferate single concentrations, okay? But if you have a network of chemical reactions, that very quickly adds up to quite messy mathematics. So let us do exactly this, and let us now apply a forward Fourier transform from 0 to infinity to both sides of these equations. So to both sides, 1 over 2 pi integral from 0 to infinity of whatever we are acting on, e minus I omega t dt. And I will apply exactly this transformation to the derivative, and of course a of t simply converts into a of omega under that transformation. So what we're going to have is 1 over 2 pi integral from 0 to infinity, and a prime of t e minus I omega t is equal minus k a of omega. So that simply got Fourier transformed. Either we chose an integral or we instructed the computer to do it, but that's just the definition. Okay, so let's follow that exact flow chart to get rid of the a prime. So once again, integration by parts. So u is e minus I omega t. I had a minus there, yeah. So du is minus I omega e minus I omega t. dv is a prime of t dt, essentially dA in this case, and therefore v is a of t. That notice is a decay function, radioactive decay or something like that. So a at infinity is equal to 0. So we have uv a of t e minus I omega t from 0 to infinity, and then minus v du, so plus I omega integral from 0 to infinity. A of t e minus I omega t dt, all of that 1 over 2 pi that we had in front there. Okay, at infinite limit, concentration's gone, it is 0. At the 0 limit, that's the initial concentration, and the exponential disappears, and so we have minus a of 0. And then here, this is plus I omega, and that is just the a of omega, and that should be over root 2 pi, so a of omega, and that is equal to this, so minus a the right-hand side of the original equation. Notice that the equation became algebraic. Right? There's nothing here anymore that is differential. And so that is one of the best properties of Fourier transform, is that it gets rid of derivatives in differential equations. So we can easily solve this for A of omega. So if we push that over there and that over here, we can have I omega plus k, A of omega equals A of 0 over root 2 pi, and this is trivially soluble for A of omega. And then, once we obtain that, an inverse Fourier transform gets us the A of t. So this is the common path through quite a lot of differential equations. Now, the interesting thing about Fourier transforms that I doubt Fourier himself actually could forecast came about with the proliferation of personal computers. Now, as you can imagine, because this gives you a frequency table, this can be quite useful. And actually, in terms of hardware devices, such devices have been around, ever since the invention of electricity, more or less. As soon as that oscillatory circuits became well understood, people realized that they can be used as digital filters. And this is our next topic, which we will only cover very, very qualitatively because, books this thick have been written on the subject, and that's digital signal processing. Now, imagine you are a singer, on stage. British stage is particularly guilty of this. And your biggest problem as a singer that you cannot sing. Frequencies coming out of your voice are, well, in the wrong place. But you have an excellent producer and lots of gigs with computers, and so what they can do is take your terrible, terrible voice, so that's the amplitude, that's the 0, and that's time, and that is something god-awful, and they can Fourier transform it into a frequency table, the so-called short time running Fourier transform. So we will have amplitude as a function of frequency, and we will have a fairly complicated looking pattern. As you can imagine, human voice is a complicated thing. And then, okay, they look at this frequency table and they say, well, really, we really like that frequency, and that frequency, but that thing really shouldn't be there. Of course, it's very easy once you've got this table to just multiply it by a function that looks like this. It's 0 where you don't want anything to sound, and it's equal to 1 where you do. And that is the most basic and by far, the most horrible possible digital filter. There are better ways of doing it, but for our illustration purposes, that would suffice. And then, of course, if that was the ft plus, then ft minus would recover a voice that is free of the undesired frequencies. You can do a little bit of surgery as well. You can cut this little frequency and shift it somewhere else dynamically so that the singing becomes beautiful. Of course, the result is what you hear on the television. Right? It's almost unheard of these days, no pun intended, to listen to the actual human voice. This is all heavily post-processed using exactly these techniques. So that is acoustics. Of course, where it came from originally was well-intentioned. If you're a radio astronomer and you're looking for specific frequencies coming from intergalactic space, what you really don't want is somebody's mobile phone to mess it up. And so digital filters, and in fact analog filters, the analog electrical circuits that behave like these Fourier transforms, have been commonly used for decades to filter out the signals that you want and to destroy the signals that you do not. Another practical example of this, interestingly, is JPEG image conversion. So you've all come across it. This is how all the images on the internet, also lower quality images on the internet are stored. But this takes us back to times like, between 1990 and 1995, where bandwidth of network connections was low, storage was not abundant, nowhere near as abundant as it is now, and image storage was a problem. Because imagine you have an image that is 1024 by 1024 and RGB, so 3 color channels, 1 byte each. That would mean 3 bytes. And so we are talking 3 megabytes of storage. Of course, the standard plastic floppy disk from 1990s, remember, was 1.44, and that was the latest generation of it, right? So the previous 5-inch disks were 360 kilobytes, and I do remember the heady days when I had to load stuff from a cassette tape on my computer, which had a whooping 48 kilobytes of memory at the time. Of course, if you have 48 kilobytes, and you need to store the most basic of images, right? Astronomers those days really had that stuff by the thousand. Right, that you have a bit of a problem. Okay, so what JPEG does is it takes your image and it converts its original RGB or CMYK, whatever it had been, into 2 channels. One is called luminosity, which is how bright the image is at each pixel, and the other is called chromaticity, which more or less, I'm simplifying here a lot, so chroma channel is which color it corresponds to. It turns out that human vision is singularly sensitive to variations in luminosity, but not terribly sensitive to variations in chromaticity. You can see that in twilight. You must have noticed that your vision in twilight is black and white. You do not perceive colors in twilight. Right? And so that is a part of the human visual perception system. We're just not terribly sensitive to precise colors. And so what this JPEG then does is it makes a Fourier transform of these images, but in both directions. So it takes the integral along the columns, and it also takes the integral along the rows, the so-called two-dimensional Fourier transform. And the result is a two-dimensional frequency table. So you have, again, an array where in this little corner there are low frequencies. And then if you go up a little bit more, there are higher frequencies in there, and even higher frequencies. And here are the highest frequencies you have in the image, frequency of color variation or luminosity variation in this case. Now, imagine you have a very smooth image, like natural environment or sky, where most of it is black and the rest of it is continuous gradients with only a few points of interest. Of course, you would be interested in keeping as little of this as you can, and there will be extremely high frequencies that would simply correspond to the noise in the image. Those you can safely ignore. And so for luminosity, we have to be careful, and so for luminosity, the compression is not that dramatic. We keep fairly high frequencies. But for chromaticity, it can be rather extreme, and you can see that in quite a lot of internet memes, right, that have been multiple times resized and recompressed into a terrible quality JPEG, where they've only really kept the lowest frequencies here, and so you have bizarre color variations and transients across the terribly compressed JPEG. That is because all of this has been ignored. And then, of course, once you store this, right, so both go into storage, the storage requirements are significantly smaller, particularly if you compress it. There are also various psychovisual enhancements about what the human eye can perceive next to what, how well. Once you need to reproduce the image, the Fourier transform is reversed and recombined into the original image that is displayed on your screen. Now, I've simplified rather a lot here. We are not talking about precisely the Fourier transform. It's one of its variations called discrete cosine transform. There are variable-sized blocks inside JPEG, so it's not compressed as a whole image. It's compressed block by little block. In the original JPEG, it was 8 by 8. In the more modern variations, it's variable. But a lot of modern image and video compression is pretty much this. And so all the blockings and all the artifacts that you are seeing are artifacts of people dropping various spatial frequencies, and the same can be done in time, so temporal frequencies as well, using all of these transformations. The other important use for this, of course, you may have guessed from the similarity of the abbreviations. It's more or less the same mathematics done by overlapping groups of people, and that is MPEG. Motion Picture Expert Group. The folks that have invented this, and that is an extension and an adaptation of that to video. But of course, the most famous part of this is the acoustic layer of this MPEG, layer 3. And what that is doing is it takes your sound signal you have, and it breaks it up into frames. It takes a frame, and frames across the signal, then runs a Fourier transform, so gets some variation of frequencies. So here, this was time, here, this is frequency, and applies quite a lot of heuristics to this. If a particular frequency is very quiet, your ear is not going to hear it. Zero out, do not stop. If you have a quiet frequency next to a very loud frequency, your perception system, because it is actually based on vibrations, of physical things inside your ear, wouldn't be able to tell, so you wouldn't hear it, drop it. If you have a frequency and it's overtones, the way human ear is arranged, there's overtone crosstalk, you can drop the overtones, so multiples of the frequency. They're all called psychoacoustics, this whole process. And so this is digitized, it's called quantization, and then compressed. So, by dropping the frequencies that a human ear is unlikely to hear, and so when it's reproduced, it's going back. Of course, you have all heard some terribly compressed sound, particularly over the phone, and you can hear that it's kind of reproduced, but there are strange bubbles and gurgles in there. That is the extreme versions of this compression, when the bandwidth is so low that the various filters begin to drop the frequencies that you can actually perceive. That's the applications. So after your practicals class, when you do Fourier transforms numerically, you would actually be able to reproduce with considerable amount of effort, but still you would be able to JPEG and MP3 compression of visual and audio data. And you now understand the quality gradations of those files. Of course, we are talking 1991 to 1995. I was your age, so I was wildly excited about all of that. These days, the modern audio and video formats are significantly more sophisticated than this, but this is a lot of relevance. Fourier transform that we call it. Okay, so the summary of the lecture, there are these wild and wonderful integrals which I haven't derived because that is a very long story that are each other's inverse, that is called Fourier transform. It's got lovely properties because it converts differential equations into algebraic equations, and it is commonly used for that reason in quantum chemistry, because a lot in quantum chemistry is differentiations that you would rather not do. And the practical engineering applications, any kind of digital signal processing begins with the Fourier transform. I've only given you the simplest and the ugliest possible way of doing that. And a lot of signal compression, both visual and acoustic, relies on a variation of Fourier transform called discrete cosine transform. And that's all I have to say. Any questions?